Precession of a gyroscope. A simple gyroscope consists of a wheel fixed to a shaft and free to spin about the axis of the shaft. That's the one. Okay, you have a rotate and you can around this one, this shaft. Okay. If one end of the shaft of a non-spinning gyroscope is placed on a support as in the figure, this is the one. Okay, and the gyroscope is released. The gyroscope falls by rotating downwards about the tips of the support. Now, let's see. Originally, it does not have any rotation, non-spin, and then you have a torque because the gravitational around this point is mgr. So when you fall, it falls down. It will rotate around y direction. Okay. It is governed by Newton's second law in angular form. Okay. We will see that. Okay. Tau equal to mgr. This is 90 degrees. It's around the y direction. Okay. Now, originally it does not move. Okay, not a spin. So L 0 time is 0. Okay, and then we will see that you have a tau. So dl is L final minus an initial is L. Should be around the y direction. So it will fall down, rotate. If you have a spin, a rapidly spin gyroscope, it behaves differently because it has initial non-zero angular momentum due to the spin. This is so initially it is I omega, we see along the x direction I. Okay, and then we have a torque around the y. This is mgr. This is a torque. So what I see is the dl have to change. The dl should along the y direction. Okay, it must rotate about the vertical axis z. I call it xyz. Originally, you spin around x axis, and you have a torque around y axis, and it turned out you rotate around z axis. So you see this one is L, rotate. dl should along the y direction in our case, torque. And at this, you look at the circle, the dl is tangent to the circle, dl. Okay, dl. Then when see what it do, initially it is around the z-axis. So this is xyz. You have an original angular momentum along x direction, and you apply a torque around y direction, and you rotate along z direction. Precession rate omega can be calculated as following. By Newton's second law, dl equal to tau dt, and the tau in this case is mgr. It's along y direction, dt. The increment angle d phi in this circle, this is angle d phi. This angle equal to the arc dl over L. So d phi equal to dl over L, and dl equal to mgr dt. And L is I omega. I is the rotational initial of this disk around x-axis, right? Omega is its angular velocity. So the precession rate omega equal to d phi dt over this one equal to mgr over I omega. When omega is increased very large, this omega precession rate is very small, decreases. Okay. This result is valid under the assumption that spin rate omega is rapid, very large. Okay. Because I is a function of m. Mass cancel out from above equation. So the omega is independent of the mass. Above equation also applies if the shaft of the spinning gyroscope is at the angle to the horizontal.